It's my pleasure to introduce our guest this afternoon, Khalid Daoudi. He's working in the French National Research Center, CNRS, doing basically machine learning and applying these days to speech and speaker verification. And Khalid is going to talk about his recent work with one of his PhD students, whom I've been on the PhD thesis, and I found it very interesting. So that's it.
Thank you, Sami. So before we get started, I want again to thank Sami for the invitation, and thank all of you for your presence, and all the others if they are somewhere else. So as Sam said, I work at CNRS, but I'm basically at the basis, I'm an INRIA researcher, but I left INRIA 4 years ago to go to Toulouse, where the weather is kind of close, Californian weather. And, but I still work with my INRIA group on a lot of aspects of speech and statistical modeling. So I will present to you here some work on sequence kernel for SVM classification of sets of vectors applied to speaker verification. And this work was mainly done by Jérôme Lauradour, my former PhD student who just defended 2 months ago, and also in collaboration with Francis Bach, who until a couple of years ago was your neighbor here at Berkeley. He made his PhD thesis with Michael Jordan at Berkeley. So he helped out on some theoretical aspects. We need some help here, please. Yeah, okay. Anyway, as I wrote on the abstract, I will use speaker verification as first a motivation to this work, and also as a vehicle to demonstrate the effectiveness of the new method that we have proposed. So speaker verification is a binary classification task where you have a set of imposter or what we call background sequences of utterance that are used for training. And then you have target speaker, for which you have only a little amount of data. And then, so you build a classifier that will score a test utterance, and a decision is made whether the speaker is the target one or an imposter. And the state-of-the-art systems are ruled by the generative approach of Gaussian mixture modeling. So basically, a Gaussian mixture model is built using the background data. So this will represent the universal speaker. This is why it's called UBM, as universal background model. And then another JMM is learned by maximum a posterior adaptation using the target speaker data. And then the decision is made by a log likelihood ratio. Okay, so, however, when you think about this problem, it's a binary classification task, so simple vector machines should be, in principle, well adapted to this kind of problem, because SVM have shown their power in binary classification problem. And this is, so SVM not only in kind of speech, but they are powerful because they have very good theoretical foundations, even though I know some people who don't agree. And not you, of course, but you know what I'm talking about. And the learning algorithms are well mastered and available, and Sami here is famous for his SVM torch. And when applied to different kind of classification problem, but static data classification problem, the results are in general very competitive and good. However, in large-scale problems in general, well, speech is not really a large-scale problem, but let's call it this way. In speech processing, SVM are not that, so far, are not that good. Why? Because in speech we deal with dynamic data, and And SVM has been built really for static data, so the extension to dynamic data is not easy. And also the size of training corpuses is enormous in speech. So as learning algorithms are at least n squared for SVMs, so this would be time and memory consuming. And in the particular field of speaker verification, SVMs, when applied at the frame level, which means that when you put all the frames, all your data in the same bag and you classify after doing some clustering to reduce the size, it doesn't work. So with Jérôme, when he started Pesci, we thought, okay, anyway, the problem of speaker verification is not to classify frames, but to classify utterance, which are sequences. And we don't care about the ordering of the sequences because we are in the framework of text-independent speech sequence. So our goal, actually, in speaker verification, if we want to use SVMs, is to classify sets of vectors. So let's see if we can build the kernels, because, of course, some kernels that will be adapted to classify sequences. I will use the word sequence because it's easier, but actually what I'm going to present is just for sequence of vector because we don't care about the real dynamic, just about the variable length. And the goal to build kernel that are similarity measured between sets of vector or sequences. So let me recall some of the basics on kernel, so I assume that people are familiar with SVM. So a kernel is similarity measure, and a nice property that is helpful in many cases from theoretical and also practical point of view is the Mercer property, which means that the kernel is symmetric and positive definite. And using the Mercer theorem, it tells that there exists an expansion phi in a high dimensional infinite space, generally unknown, called the feature space, in which the kernel K is a dot product. It can be written as dot product in this feature space. And this property is the one that allows SVM to work because it maps a linear problem to a nonlinear one by mapping the data in this high dimensional feature space. So if somebody is not familiar on SVM, just stop me and I can spend 2 minutes on it. Anyway, the key for SVM is kernels. And our goal is now to build kernels that measure the similarity between sequences. So in the literature, there exist 3 families of sequence kernels. They are listed there. And here I'm talking, of course, only about continuous data. I'm not talking about string kernels or kernels about graph, but on continuous data. So there are 3 families. The first one is the so-called mutual information kernel, which are based on the availability of an a priori probability distribution of the data. The second family is kernel between probability densities, which means that you have a sequence, you estimate probability distribution, and then your kernel is a kernel between 2 probability distributions. And the last family is combination of vector kernels, which is basically you combine your frame level values of kernel the way you want and the way it could work. Okay, so this is I said already, but just for the specialist of speech, that here the definition of sequence is value set of vectors, and we use the same speaker, a sequence from the same speaker, same recorded session. Okay, so let me give a brief overview about all the kernels that are used in speech speaker verification. So there has been, so the first one is probably the most known of sequence kernel, probably the first one, is the Fisher kernel, which has actually been shown to be an approximation of mutual information kernel. And 2 or 3 years ago, there has been a thesis by somebody from Sheffield University called Vincent Wan, who made a very nice thesis on the application of a Fisher kernel to speaker verification. And the Fisher kernel is here. It's a normalized dot product between Fisher expansions, which take the likelihood gradient with respect to the parameters of the UBM. So, if you remember, with respect to with respect to the parameter of the Gaussian mixture model, the UBM. And so you can guess, especially that systems that work well, GMM-based system that works well in speaker verification, they are huge. So if you take the gradient about all the parameters, your expansion is huge. So, and the result of the thesis was that it doesn't really give better result than just classical GMM, and it's very computationally consumed. So this is just to show, we'll skip this, how Fisher expansion works. Go to the other family of kernels that have been used in speech. Well, the first one, it's Jérôme who used it. It hasn't been done before, but anyway. So the probability product, it's the kernel between probability densities. So, for example, the probability product kernels, which are, which are here. It just from a sequence, you do a learning to estimate the 2D distribution, and then the product kernel between the distribution is given here. And for a Gaussian mixture model, you can have an analytical form if the degree Q is 1. And this is just used for more robustness when you apply it. And Jérôme has tested this kernel for speaker verification. The other kind of kernel between probability densities is the exponential embedding of divergence. So it is analogous to the Gaussian kernel. So you take the 2 distribution, you have or distances have to be symmetric, of course, and you exponentiate it and you get a kernel. And recently, just a year ago, in last ICASP, William Campbell and his colleague have developed, using just a very simple approximation of the Kyle divergence, they come up with a kernel called supervector GMM, which is basically, for each sequence, you estimate using maximum a posteriori adaptation, you estimate a Gaussian mixture model using the UBM model. And then you just construct the supervector by stocking all the means of the Gaussians. And then the kernel just a normalized that product. But the problem, of course, is that every time you need to estimate a Gaussian model in training and, of course, in test. So, and the other kind of kernels, the other family is when you just compute a function of enter and intra sequence frames or elements. And a simple example is just the linear combination, taking just the mean over all the possible 2-element kernel values. However, the problem of such kernel is that the complexity is t² for each kernel computation, and for applications like NIST ones, it's impossible to use such kernels. So another famous kernel that actually motivated our work is the so-called Generalized Linear Discriminant Sequence kernel, or GLDS kernel, which is defined this way. The motivations are, I'm not going to, she's defined here. It's just, so phi is a polynomial expansion. So you expand all your frames or your acoustic vector here. You take the mean, so using an expansion of degree Q. You do the same thing for the other sequence, and then you normalize by the matrix of second moments. And as you see, it's a dot product between these two. It's a normalized dot product between these two expansions. And I remind that this is a polynomial expansion. You take all the monoms of degree less or equal than Q. So this kernel was motivated by an idea or principle that you build a discriminative model on a sequence and you score on the other, and then you do some approximation to make it symmetric. But I prefer to see it because since I've been starting talking, you heard the word normalization all the time. So I see it because it's necessary because you give the same importance to all components in this unknown feature space that you don't control. So the advantage of GLDS kernel is that it and of this explicit expansion, because now you explicitly map to the feature space, so now you know the feature space, it leads to high efficiency during tests because you just use afterwards a linear SVM model. However, the problem is that you cannot use high degree expansion, and in practice you cannot go more than 3 because it grows geometrically, the size of the feature space. So this was our question. Could we consider this family of kernels and see if we consider any expansion phi that defines a Mercer kernel, which can be probably unknown, and see what can come up with from such family of kernels. So now I go to the new family of kernels that we have developed. And you see here, so we are just taking again the GLDS kernel form, but now we are considering any Mercer expansion that defines a Mercer kernel, or that is defined by a Mercer kernel, a normalization matrix with the second moment matrix of the expansion phi. We add a regularization term because it is necessary from theoretical point of view, also numerical, because if the dimension of the potentially unknown expansion is high, very high, or infinite, so this matrix won't be invertible. So you add this regularization term to make it invertible. And our goal, of course, is to kernelize this expression, is to compute this without necessity of having access to phi, just using the kernel trick. Another nice also extension of GLDS kernels is instead of considering the second moment matrix here, if you use the covariance matrix. And why this is interesting? Because it gives another interpretation to this family of kernels, since, as you may know, that any kernel defines a distance, and if you compute, it's easy, just 2 lines of computation, the distance associated with this kernel is just the empirical Mahalanobis distance between 2 Gaussians in the feature space. So in other words, if you use the covariance here, you are ending up computing a kernel between probability distributions, Gaussian, but in the feature space. And this is kind of interesting because, well, it depends on who, because in many algorithms such kernel PCA or whatever, you can, the hypothesis of Gaussianity in the feature space is used. So, yeah. Yeah, sorry. I have to repeat your question they asked me. So why do I need the regularization term when the covariance is there? It's just because, as I said, it's from theoretical point and also numerical point of view. And as you will see, this epsilon is going to disappear. But here it's just to do the generalization with the covariance matrix. And from a practical point of view, if you use the stuff as it is, sometimes from the numerical point of view, this covariance is not invertible. If you have tried to invert to really, from numerical point of view, covariance matrix, sometimes even though for no reason you have to add this epsilon at the diagonal. But I see your point. Okay, so yeah. So I was saying that with this we are now having a kernel between probability distributions in the feature space. Still have. Okay, so this is one of the major theoretical results. So is that we could prove that we can rewrite these kernels in a dual form, or give a kernelized form this kernel. So this is the original kernel. So this is when there is no regularization, assuming that SV is invertible. And actually, even though it's not, the expressions hold with the pseudo and inverses. And you see that the dual form involves the gray matrix, which is not surprising, and the so-called empirical map, which is just the start vector of the value of each element of the sequence with the training data. In the case you have the regularization term, you need to make an hypothesis which is kind of weak. Actually, if the hypothesis is that all the expansions lie in the span of the background data. So if your background data, actually I shouldn't have training. If your background data are your training data, so this condition always holds, because you always work in the span of the training data. But in our application, it's not the case. The background data are not the training data. They are just subset of the training data. So this condition may not hold, but if you have a large corpus and large corpus data, so you can assume this condition. But anyway, in our application, this epsilon is going to disappear. And if you use the covariance now, so the Mahalanobis sequence kernels, you have just to insert a projection matrix here. So this is the first theoretical result. And here comparison of the complexities from between the original form and the dual form. So you see that we have achieved what we wanted so far, is that just the D is the dimension of the feature space. Now we replace it by N, which is the size of the background data. So the advantage is that now we can use any kind of expansion, including infinite one, associated with the Gaussian kernel, for instance. But the problem is that we still have something that we cannot use here in practice, because the size N of background is very huge. So our objective is to find an approximate but tractable form of this dual form. So I'll go to find an approximate, appropriate approximation. So I said I'm going to reduce. If I come back here, you'll see that what makes the things here n or n squared is the size of the Gram matrix and size of this empirical map here. So our goal is to reduce the size of the empirical map, but still keep a maximum of information. And for many reasons, we chose the incomplete Cholesky decomposition to achieve this approximation. So the incomplete Cholesky decomposition acts this way. It selects a code book from the original set B of background data. And if I is the index of this book, so the approximation is given this way of the gray matrix. And the ICD minimize the difference of the trace between between the Gram matrix and its approximation, and it's easy to show also that it minimizes the mean square error. And the trace, this trace here is actually a norm on a matrix is defined and positive. It's not a norm for for matrices, but for this particular class of matrices. So it's a good approximation. It's a good criterion for approximation. And also, a nice thing is that at no time we need to store the full grain matrix, which is n squared, to compute its approximation. There is an algorithm developed recently by Francis Bach and Michael Jordan, which allow to compute the ICD without storing the full matrix. It's an algorithm linear in n. And of course, this stuff you do it offline. So here is a little example of what the ICD does. So the blue point are the training data, and the red is the result of an ICD using a Gaussian kernel. So it does a kind of clustering that spread all. You have a question?
Yeah, the two clusters, does that correspond to like the same speaker, different speakers, or is that like male voices and female voices?
Oh, your sentence is long and I have to repeat it here. So the clusters correspond to?
Well, the distribution up there is bimodal, and I was wondering what the two modes are.
Yeah, so the distribution of the blue is bimodal, and you were wondering what the two distribution are. So I don't know exactly, but I guess it should be two Gaussians or something. But this is just a toy example.
Okay, this is synthesized data, not the voice data.
No, this is not voice data. This is just a toy example.
Oh, okay.
Just to show what kind of clustering ICD does. Okay, so the second theoretical result is using the ICD approximation, we have a new form of the kernel, which resembles to the old one, but now we have reduced the size of the empirical map and the size of the normalization matrix. And we moved from n squared to m squared, where m is the size of the codebook. And of course, this is a trade-off parameter that you have to tune depending on the efficiency and the approximation you want to achieve. Okay, so now I move to the application of these sequence kernels to speaker verification and see what's going on. So the development corpus is used the NIST speaker regulation evaluation data of 2003-2004. So half of the corpus is background data, and the other half is for validation, so to tune the hyperparameters for the kernels and for SVM, and to choose also the decision threshold. And the evaluation is on the NIST 2005 SRE. And the evaluation is, of course, given by NIST as by the detection cost function, which is so this is the pre-processing. I don't think that this is important. And here, first result on the development data. So first, we want to know, in practice, what kind we have defined the family of kernels. So how from experimentally have a hint on what should we choose in all these parameters. So, and the results showed that with centering, so using the covariance matrix, there is no significant gain. And this is probably because the data are already centered from the beginning. And the other important result is that the regularization degrades. And the reason why is that now we are not using the exact form, of the kernel, but with an approximation. And actually, the ICD does already a regularization. So this is why we don't need anymore the epsilon term. So in summary, no centering and no regularization. Now how to choose and tune the vector kernel that defines the map phi. So our best results were obtained with a Gaussian kernel, but using a good spread parameter. And what was nice is that the one that works well all the time is the one which have a theoretical motivation that I don't remember the name of the author of the paper, but in this paper, the author said that the good value for O should be this one with the dimension, and sigma is the variance of the data. It's the mean of the variance of the data. So now the size of the code book. So probably I go fast. So yeah, I mean, if you are familiar with that curve, you understand. Otherwise, what you should look at is the equal error rate and the DCFs. And the lowest they are, the better the system is, of course. So, so on the choice of the codebook, as I said, so M is trade-off parameter that you have to tune, because as big as M, the more M is high, the more your approximation is good, but the more your but the less your system is efficient. So we tried many values of M on development corpus, and you see that the score always, the performance always improve until a certain point where they become flat. And this is nice. This shows that at certain point we achieved a good, very good approximation of the Graham matrix. So in all the experiments I'm going to show later, we chose M around 5,000 elements of the code book. So now the evaluation. So here, so probably we don't need to look at this. So now it's the real evaluation on NIST 2005. And here we compare our U kernels with the GLDS one and state-of-the-art UBM GMM, which is using a toolkit for UBM GMM that is available, that has been made available at University of Avignon, who are one of the best teams in France in speaker verification. They are always from the best in NIST evaluations. So, and before that, I don't have the picture slide here, is that we checked that GLDS gives exactly the same result when you use a feature space Mahalanobis sequence kernel with a polynomial degree of 3. So it means that it validates the theoretical result. And you see that the new kernels are much better than GLDS one, and they are competitive to state-of-the-art UBM GMM. And let me just check. Now, of course, the best system in all NIST evaluations use fusion. So it's all time many systems, and at the end you combine them. So here you have again the three systems, basically GLDS, FSNS, and UBM GMM. And the fusion between 1 and 2 doesn't improve, which is not surprising because they exploit the same information. They do almost the same thing. But when we fuse any SVM with the UBM, with the GMM, it improves. And the best one, of course, is the one given by the fusion of our system and the classical UBM GMM. So the conclusion is that there is a significant gain in discriminative generative fusion. Now it's the evaluation of all the kernels that I have talked about so far. Probability product kernel, GLDS, Fisher kernel, FSNS, UBM, and the support vector GMM. And so you can see that the best results are given by the super vector GMM, the approach that just stacks all the means of GMMs in one vector and do normalize that product. But of course, its complexity is higher than ours, but still it is the one that gives the best results. And our system comes just next. And the others, Fisher or probability product can't really do give bad results. So again, the fusion is the best system is obtained by fusing 1 and 3, which is FS and S, and supervector GMMs. So so what? How much? I don't know when it's okay. So in conclusion, so we have made a theoretical and experimental exploration of sequence kernels, or kernels between sets of vectors. I'll see that there is many possibilities of sets of kernels, and we developed a new family of sequence kernels that we have experimented on benchmark NIST evaluations, and the best performances was obtained by the combination of this family of kernels and the GMM supervectors, which is a very recent method that shows effectiveness in speaker verification. So, of course, there are several ways to improve SVM for speaker verification. This is one, but there is a lot to do. One weakness of all margin classification method is that it's not easy to adapt the classifications to new data, which generative approach do easily. So model adaptation is something that is really of big need to in large margin classifier. Well, for speaker verification especially, so another thing that could be very helpful is to use string kernels to add high-level feature to the system, because the specialists know that high-level features that prosody and everything can improve the performance. The other thing is I forgot to say that all the results of the UBM GMM system are obtained using so-called T-norm, which is a normalization of the scores and which improves a lot GMM with. But this T-norm, or this normalization of the scores, are based on the fact that the scores are probability outputs. But as you know, the output or SVMs are not probabilities. And the question is how to handle these scores, how to build a score normalization which is appropriate for SVM. This will also, in principle, improve the result, because analogously to GMM, all kind of normalization are necessary to in state-of-the-art system. So I think I think I probably go fast. Thank you.
We have time for a few questions, but let me first remind you that this presentation is videotaped and will be accessible on the outside Google. So please keep your question at a level which can be heard outside Google.
So no confidential questions and no confidential answers.
So when you treat sequences as sets, that means you throw out any ordering information?
Yeah. Oh, sorry. Yeah, when I consider sequence, but it's just a language abuse. I said it in the beginning. What I call sequences, they are sets of vectors, and we don't care about the ordering because we are on text independent task. But if your question, I'm going to pose the question yourself. What do you do when you have dynamics? This is your question.
So is there something to be gained by looking at the dynamics? Maybe
to be gained, I mean,
maybe in this problem, maybe in other problems.
No, in another problem, actually, this is a problem that interests me a lot, is how to handle really true dynamic. For example, how to use SVMs in speech recognition. And the problem here is that you don't, if you want to apply this, you're not anymore just in classification, but you're doing segmentation. And this is something that large margin classifiers cannot do so far. But there are some, for example, the Fisher kernel, or all the kernels that are based on generative models, on probability distribution, you can use them to, the Fisher kernel, for example, it just requires the likelihood of the distribution on your observation. So you can take into account the dynamics. The problem is how to segment. And I think there was some paper of PhD done with Mark Gales from Cambridge University in UK, where they apply SVMs using Fisher kernel for speech recognition, but just for letter recognition, so they escape the true problem. But if you have any ideas on how to handle the dynamics, you. Thank you very much. Thank you for being here.